చూడమ్మో నువ్వు పెట్టిన దాంట్లో చూసి
Right. Good morning, everyone. Am I audible, ma'am? Is my voice?
Yes.
Am I audible?
Yes, sir.
Okay. Right. So now in the last class, we completed the second module. Today we are going to start the third module. So third module discuss about the DC machines. Right. Can you define a machine? And what is a machine? So machine అంటే ఏంటి? So right. So machine is a device which performs a particular task. So particular given task, right? So now, so this machine will take certain input and gives an output. Unmute చేయండి. Unmute చేయకండి. Right? So this machine will perform a certain work by taking certain input. Now, what is an electrical machine? So in electrical machine is nothing but, so here, as I said here, say a machine will be having certain input or certain output, right? So now if the input or output is electrical energy, so either input or output, so any one of these two is an electrical energy, so then this machine we can call it as an electrical machine, right? So now if this electrical energy is there at the input, right? So electrical energy, if you are given as a input and you are getting output as your mechanical energy, so in such a case, so the machine is called the motor. Okay, so if the machine takes the electrical input and gives mechanical output, in such a case, that particular machine you can call it as motor. Now if the same machine takes input as your mechanical energy, so if the mechanical energy is taken as input and if you are getting electrical output, right? So electrical output, then this machine is called the generator. Okay.
Generators and DC motors.
What more?
Yes, sir.
F6. Okay, right. So depending upon whether input is electrical or output is electrical, you can define the whether it is the machine as either motor or generator, right? So if the machine is taking electrical input and giving mechanical output, that machine you can call it as motor. So if the machine is taking mechanical input and giving electrical output, then you can call it as generator. Okay. Now, as you know, this electrical energy again of two types. Okay, one is DC, another one is AC. So DC energy, DC in the sense direct current, AC in the sense alternating current. Okay, so there is the representation of the DC will be like this, and alternating current will be having its magnitude changing with respect to time. So for DC, the magnitude will be constant. Okay, so now if this electrical energy, as I said here, so in case, so the input is electrical energy and this electrical energy is a DC electrical energy, then in such a case the motor is called the DC motor. So if the input is AC electrical energy, in such a case, you can call it as AC motor. In similar way, generator also the same. So your electrical output, what you are getting is a DC. In such a case, this generator is called a DC generator. If it is AC, it is called the AC generator. Okay. So now in the third module, we are going to discuss about the DC machines. Okay. So machine, as I said, this machine in the sense, it may be either motor or generator. Okay. So depending upon which energy you are giving as input, you can define that machine as either motor or generator. Okay. Simply suppose if we are calling DC machine, that DC machine in the sense, it may be either a motor, either a generator. Okay. So now in the third module, we are going to discuss about the DC machine. That means DC machine may be having a DC motor as well as DC generator. In the first part, we are going to discuss about the DC generator. In the second part, we are going to discuss about the DC motors. Okay. So in the DC generator, we are going to study the principle of operation, then the construction and the EMF equation, types of generators, losses and efficiency. So in a similar way, in DC motors also, we will discuss the same. So what is the principle of operation of DC motor? What is the back EMF? So what is the torque equation here? Okay. Then types of DC motors, losses and efficiency. Okay. So in the first minute, you are going to get up to the DC generators only. Okay. So today in the afternoon session also, instead of lab, I am going to take the theory session only, so that we can complete this DC generators topics as early as possible. Okay. Right. So now the operation of these machines, these electrical machines, depends upon the understanding of magnetic fields. Okay. So you should have the certain basic knowledge about the magnetic field energy. So in such a case only you can understand these electrical machines, right? From our lower classes, we can recall some of the fundamental concepts regarding the magnetism, so that we will proceed further, right? So what is magnetism? Magnetism. So magnetism ante entama. So as you already know, so you can talk. So I will. So anybody, you can unmute and you can talk. So in lower classes already you know about these magnetism, the fundamentals of magnetism. So if you take a magnetic pole or magnet simply, right? So this magnetism, so it is the property of a body. Okay, magnetism is the property of a body. So because of this property, that body will the body will have the tendency of either attracting or repelling these iron parts. Okay, so magnetism is the property of a body by which it may attract or repel some other metals, you can say, right? So now magnet. So magnet is it is a device. Okay, so magnet is a device which is having the property of magnetism, right? So there are different types of magnets are available. So round shape you are having, it may you are maybe having bar type magnets are there, U-shaped magnets are there. Okay. So now if you see the magnet, every magnet will be having two poles. So one pole is north pole, another pole is south pole. North, south. You know already all these, right? And this magnet will have the magnetic lines. So magnetic lines of force will be there. So those magnetic lines will be flowing from north to south, outside the magnet. Okay, so like this, north to south. The direction of magnetic lines will be from north to south, outside the magnet. Okay, so now inside the magnet it will be from south to north. Okay, so inside the direction will be from south to north. Outside, the direction of magnetic fields will be from north to south always. Okay. Right. So as you know, these magnetic lines, you can also call it as magnetic lines of force. Okay. You can call these as magnetic field lines or magnetic lines of force. So you can call it any term. Okay. Either these or these. Okay. Now these magnetic lines of force, if you observe, so those are closed loops. Okay, you see here, so it is one magnetic line. If you observe, it is looking like a closed circle or closed loop, right? Okay, and these magnetic lines will be looking like a stretched rubber band. Okay, so if you stretch the rubber band, so in a similar way, these magnetic lines also will behave. Okay. Right. As you know, so the north and the north poles, same poles. If you take same poles, will be repelled, and opposite poles will attract. Okay, right. So then, what is the magnetic field? What do you mean by magnetic field? So the magnetic field is nothing but it is the space around the magnet. If you take a magnet, let us take a magnet which is having north pole and south pole. Now, around this magnet, you have if you take certain space. Okay, so the space around the magnet up to which the influence of this magnet is there, right? So suppose if you take some metals, now if you put in this region, this may either attract or repel this metal piece. So that means the influence of this magnet is there up to this point. Now if you take a metal here, so it may not either attract, either repel this element. Why? Because it is the outside the field. Okay, so what is this field? Magnetic field is nothing but it is the space around the magnet up to which this influence of magnet is there. Okay, so this is called the magnetic field. Now this magnetic field will be represented with the lines of force. Okay, these lines of force will be distributed up to that space. Okay, so like this. So inside also you will be having inside from south to north, on the outside it will be north to south, like this. Okay, so the space, the area or space around the magnet up to which the influence of the magnet is there, so that space you can call it as magnetic field. Okay, now this magnetic field, that space is entirely represented with these lines of force. Okay, and so because of that reason, this magnetic field you can also call it as total number of magnetic lines in a particular space. Okay, so now this then you have another term, magnetic flux. So this magnetic flux is represented with phi. Right, so magnetic flux is represented with phi. Okay, so this magnetic flux represents the total number of magnetic lines of force. Okay, total number of lines of force or magnetic lines of force in the magnetic field. Okay, now if you see in this magnetic field, how many lines of these magnetic field of force is there, so that count will be represented by this magnetic flux phi. Okay, so generally this phi is represented with the units Weber. So Weber is the unit for magnetic field. Now 1 Weber is nothing but 10 to the power of 8 lines of force. Into classes first year ka అంటే ఫస్ట్ ఇయర్ దానికి క్రియేట్ చేయలేదు అనుకుంటాను. ఇప్పుడు వరకు అయితే జరగలేదు అనుకుంటా. ఒకటైతే ఆఫ్టర్నూన్ క్రియేట్ చేసి ఆఫ్టర్నూన్ సెషన్ పెడుతున్నాం. అవునా? పోనీ నేను కాసేపు ఈ క్లాస్ అయిపోయిన తర్వాత మీకు లింక్ పెడతాను. ఆఫ్టర్నూన్ వాళ్ళకి క్లాస్ పెడతాను. Okay, right here. So this magnetic flux is represented with the phi. Now this magnetic flux of phi is nothing but total number of lines of force in the magnetic field, right? So total number count, right? Now the unit for magnetic flux is Weber. Now 1 Weber is nothing but 10 to the power of 8 magnetic lines of force. Okay, if there are 10 to the power of 8 magnetic lines, then you can call it as the magnetic flux within that space is 1 Weber. Okay, so this is the main thing. Okay, so now if you take a conductor, so now this is one conductor. Okay, so now this representation of conductor may be like one circle also, right? Like this also you can represent now. Okay, so these are the circles you can call it current conductors. That means it may be having like this, but only will represent only one circle. Okay, so while drawing the diagrams, you may represent the conductors are like circles. Sometimes you can even represent like this also. Okay, so now whenever a conductor carries the current, okay, if the current is flowing through this conductor, magnetic field will be developed across this conductor. Okay, so if you take one simple conductor, so here I'm taking, so this is, if you take this conductor, now if the current is going inside, so then you can represent with a dot. Okay, so if the current is going outside the towards the observer, so then you can take it as cross. Okay, like this. So a conductor is represented with one circle. Now inside, if you are having dot, that means that the current flowing in the conductor is away from the observer. So that means inside the paper. Sorry, I'm taking in opposite, right? If it is dot, it is towards the observer. If it is cross, then it is away from the observer. Now, if any conductor, if it carries the current, so then magnetic field will be developed across this conductor. Okay, so now this magnetic lines of this magnetic field's direction will be given by right hand rule. Okay, so you can use the right hand rule to represent the direction of this magnetic field, right? How you can you just hold your your conductor, you hold your conductor in your right hand, right? So such that the thumb will be pointing. So thumb will be pointing the direction of your current, and the curled fingers will represent the direction of flux. Okay, so now if you take this conductor, so which is carrying the current towards the observer, that means your thumb will be towards the observer. Now the curled fingers will represent the direction of current. That means, so this may be, okay. Now if it is cross in a sense, so that direction of magnetic field will be inside the paper or away from the observer. That means if you take your thumb inside the paper, right hand thumb, and the curled fingers will represent the direction of magnetic flux. That means this direction will be in this direction. Okay, so the direction of magnetic field will be given by this right hand rule. Okay, so whenever current flowing through the conductor, magnetic flux or magnetic field will be developed. That direction of magnetic field will be given by this right hand rule. Okay, right now. So now if you are having two magnets, okay, suppose if you are having the two magnets, now there exists a certain force between these two magnets depending upon the type of the pole. Okay, now if there is this side you are having north pole and sorry, south pole, on this side north pole. Now these two will attract each other. Okay, so that means there is a force of attraction. The force of attraction is there between these two magnets. Now if your same poles are there, we keep same poles. Now there will be a repulsion force of repulsion, or repulsive force will be there between those magnets. Okay, I think all these concepts you already know from your lower classes. I just recalled. Okay, here if you're having any doubts, you ask me. Okay, shall I proceed to our main topics? So now you come to our main topic, DC generators. So principal operation we will discuss. Okay, right. Principle of operation of DC generator. Okay, so now all the generators will work on the principle of dynamically induced EMF. Okay, so dynamically induced EMF. So this is the principle of operation of generators. Okay, so this dynamically induced EMF is nothing but, so this is the Faraday's law of electromagnetic induction. Right, so the generators will work on Faraday's law of electromagnetic induction, or you can say it is the principle of dynamically induced EMF. Okay, so now what is this Faraday's law of electromagnetic induction? Okay, so this law is developed by the scientist Faraday. So according to his name, this law is defined as Faraday's law of electromagnetic induction. Okay, so now what this law will state? Okay, so this law states that, so whenever the flux linking with the conductor or coil changes, an electromotive force, so which is nothing but EMF, simply you can call it as EMF. So EMF is set up in that conductor or coil. Okay, so now actually what this Faraday, the scientist Faraday has done is that he took one magnet. Okay, he took one magnet and he took one coil. Coil is nothing but it will be a conductor which is having closed path. Okay, so you have here this magnet will be having the magnetic flux. Okay, so here magnetic flux will be there, right? Now what he has done is he fixed this pole to he fixed this pole and he moved this coil. So coil or conductor. Okay, so now if we keep fixed this pole, so you are not going to move this pole, we are going to move only the coil. Okay, so continuously he is moving inside the magnetic field. Okay, in such condition he observed that the current is flowing in the coil or conductor. Okay, so what it means, so now whenever you are moving the conductor or coil, in the sense the magnetic flux linkage we are changing here. Okay, so see here, like this you will be having the magnetic lines. Okay, like this. Now if your conductor, if you observe, when you move this side, the lines of magnetic flux linking with this conductor or coil will be decreasing. Now if you move towards the magnet, then the lines of flux linking with this conductor will be increasing. Okay, that means there is a change of flux is there, change of flux linkage is there between this magnet and the conductor, then there is a motion exist. Okay, so between the two, right? So what he has done, this magnetic field is fixed one, but we are moving this conductor. Okay, whenever you are moving this conductor, the flux linking with this conductor is changing, and in such a case he observed that current flowing through this conductor or coil. So he has given that one statement that whenever the flux linking with the conductor or coil changes. Okay. So now if your conductor, if your conductor is having a closed loop, current will flow. So but if you are having one simple conductor without having any closed loop, so in such a case, EMF will be developed across the conductor. Okay, EMF will be developed across the conductor. Okay, if you take one single conductor and you move inside the magnetic field, then he observed that some EMF will be developed in the conductor. Now, when EMF is nothing but voltage, now simply you can call it as voltage. Okay, so now whenever if you close that conductor, then the conductor current will flow. Okay, so now according to this Faraday, he has given one statement and called this statement as a Faraday's law of electromagnetic induction. According to this, whenever the flux linking with the conductor is changing, okay, so whenever the flux linking with the conductor or coil is changing, an electromotive force, so which is EMF or voltage, EMF will be set up inside the conductor or coil. Okay, so this is the principle of operation of DC generator. Okay, so now how you can achieve this change in magnetic flux? Remember now, the flux linking with the conductor or coil must be changing. So this is the important thing. Okay, so there must be a change of flux. Now how you can achieve this? So the change in the magnetic flux associated with the conductor can exist only when there exists a relative motion between the conductor and flux. Okay, so relative motion in the sense, so any one of those two has to be moved, right? Or if both are moving, if the both are moving, in such a case, at least some relative speed must be there between the two. Okay, so if it is rotating at 100 speed, if it is also rotating at the 100 speed, so then there will be no EMF will be induced. So, but if it is rotating at less than certain speed, in such a case, you may be observed some EMF induced in this conductor. Okay, so if it is the pole, it is a conductor. So there must be some relative motion must exist. So between the conductor and your magnet to get the EMF between the conductors, right? So this relative motion, how you can achieve? So you can achieve either by rotating the conductor with respect to the flux, or by rotating the flux with respect to the conductor. Okay, so now you can rotate the conductor, or you can rotate the magnetic flux to get the relative motion. Okay, so to get the relative motion between the conductor and your magnet, you can move any one. Okay, you can move the conductor and you can keep the flux as constant, or you can fix the conductor and you can move the flux. So you can do anything. In both the cases, this law will be valid, and EMF will be induced in the conductor. Now here, if you see here, as I said before, this generator works on the principle of dynamically induced EMF. Okay, dynamically induced in the sense the conductors are rotating. Okay, so now if you rotate the conductors, then in such a case, the EMF induced in this conductor is called dynamically induced EMF. Now, if you fix the conductor and if you are rotating, or changing this magnetic flux, then in such a case also the EMF will be induced in the conductor. But in such a case, that EMF is called the statically induced EMF. Okay, statically induced EMF if your conductor is stationary and flux is changing. Right. So in both the cases, EMF will be developed across the conductor. So EMF is nothing but voltage, right? So this voltage will get generated in the conductor as long as there exists a relative motion between the conductor and magnetic flux. Okay. So now such an induced EMF, which is due to the physical movement of coil or conductor with respect to the magnetic flux or movement of flux, it is called the dynamically induced EMF, as I said before. Okay, so if you are rotating the conductors, the EMF induced in the conductors are called dynamically induced EMF. And if you are rotating the magnetic flux and if you are fixing the conductor, then the EMF induced in the conductor is called statically induced EMF. This generator, DC generator, works on the dynamically induced EMF, which is nothing but flux is constant, flux is stationary, conductor is moving. Simple. Okay. So you have to remember the key point here always. Okay. So for generating action, that means for the EMF to be induced, what is the required? You must have the conductor. Okay, conductor or coil. So to get an EMF induced or for generating action, what are the requirements? So what are the basic components we must have? The first one is conductor or coil. Okay, second one is magnetic field or flux. Okay, so third one is relative motion between the conductor and magnetic flux. Okay, so three points must be there. So there must be a conductor or a coil, and there must be certain magnetic field. This magnetic field will be obtained by either electromagnets or permanent magnets. Okay, so now between these two, conductor and magnetic field, there must be a relative motion. Okay, if there is no relative motion between the conductor and coil, so between the conductor and magnetic flux, then there is no EMF will be induced. That means no generating action. Okay, so for getting the EMF to be induced in the conductor, so there must be some relative motion between the right. So this is the principle of operation. Now let us understand this principle of operation by considering one single loop. Okay, so single loop in the sense here we are going to take two conductors. Okay, two conductors. One is AB and another conductor is CD. So two conductors we are taking and we are making one closed loop here. So to get the current flowing between the two conductors, there must be closed path. Okay, we are making some closed path here by connecting these two conductors like this. Okay, it is like a rectangle loop. Okay, rectangle coil also you can say, right? So now this arrangement we are going to fix inside a magnetic field. Okay, so here you have the north pole, here you have the south pole. Now, as I said before, there will be a magnetic field between the north and south pole, right? So magnetic flux lines of force will be in this direction. Okay. So now some EMF will be induced in the conductor whenever there exists a flux linkage with respect to these conductors. Okay. Now how this happens, let us see here. Now in the figure we are considered a single loop conductor, so which is of rectangular shape, and it is placed between the two opposite poles. Okay. So now the rectangular loop of conductor we are calling it as ABCD. Right. Now this loop or coil we are going to rotate with respect to this axis. So AB. So you are having AB axis, right? So which is represented with dotted lines. Okay. With respect to this axis, we are going to rotate this coil, right? So in such a case, so now if you are rotating in this direction, so your AB conductor will be moving this side, and CD conductor will be moving this side, right? We are continuously moving inside the magnetic field. Okay. So this ABCD coil will rotate inside the magnetic field about its own axis, which is that axis is AB. Okay. So now when the loop rotates from its vertical position to its horizontal position, right? So now it is in vertical position. So now after 90 degrees, it will be horizontal. Okay. So now if you see here, it is in vertical position. Now if it is moving in clockwise direction, after 90 degrees rotation, this will come to come in parallel to your flux lines. Okay, so during in such movement, so these conductors AB and CD both will link with the magnetic flux. Okay, so when the loop rotates from its vertical position to horizontal position, it cuts or links, you can say, right? It cuts the flux lines of the field. Okay, so now whenever it cuts, there is a magnetic flux linkage will be there, right? So now if there is a continuous movement between this linkage, suppose if these flux linkages are changing, according to Faraday's law, EMF will be induced in the conductor, and if there exists a closed path, current also will flow. Okay, so that based on that principle we are working here. Okay, so as during the movement, this movement, so two sides in the sense, here AB and CD, so these two are the conductors. So these two conductors will cut the magnetic flux, and there will be some EMF induced in the both sides of the loop. Okay, so now whenever these conductors, this loop is moving from vertical position to horizontal position, in during that moment, they will cut the magnetic flux. So now according to Faraday's law, so there exists some magnetic change in magnetic flux linking with the coil or conductor. So EMF will be induced in the both the conductors AB and CD. Okay, so now after 90 degrees, your coil will be like this now. Okay, AB here, it will get it will be aside of your south pole, CD will be aside of your north pole. Now if you observe, now here your rectangular loop is in parallel with the magnetic flux lines. Okay, so when now in such case, if they both are in parallel, in such case there will be no EMF will be induced. Why? Because no flux linkages will be there if magnetic flux lines and your loop both are in parallel. Okay, right here, let us see here. So as I said, whenever it is moving from vertical position to horizontal position, EMF is induced, right? So now whenever there exists a closed loop, so there will be current will be flowing inside the conductor. Okay, now how will be the direction of current? So how will be the direction of current? That the direction of current, it is given by the Fleming's right hand rule. Okay, so direction of your current is given by Fleming's right hand rule. So what is this Fleming's right hand rule? So if you see the Fleming's right hand rule, so this rule states that if you stretch your right hand thumb, if you stretch your right hand thumb, index finger and middle finger, okay, so thumb, index finger and middle finger of your right hand perpendicular to each other. Okay, so first three now. So your thumb, next index finger and middle finger, right? So you have to stretch all these in mutually perpendicular direction. Okay, so that means this may be either inside this paper or outside this paper, you can say. Okay, so this is thumb, this is magnetic. So this thumb will be pointed towards the motion of the conductor. Okay, we have to place this direction of thumb as direction of your movement, and you have to place this index finger in the direction of your magnetic field. In such a case, this middle finger will represent the direction of current flowing through the conductor. Okay, right now. So as I said in the previous slide, if you observe the previous slide here, okay, so when this, I will erase this so that you can understand, right? So now this is the rectangular loop. Okay, so now this rectangular loop is rotating about this AB axis. Now it is in vertical position. Now after some 90 degrees rotation, it will come in horizontal position. Okay, Now, while moving from vertical position to horizontal position, it will links with the flux between this north and south poles, or it cuts the magnetic flux, right? So now, when in such a case, EMF will be induced across the two conductors, okay, AB and CD, and that if there is a closed path here, so because of that EMF, current will flow. Okay. Now that direction of current is given by the Fleming's right hand rule, right? In Fleming's right hand rule, you have to take your right hand and you have to take first three fingers, right? Thumb, index finger, and middle finger, right? Now those three fingers, thumb, index finger, and middle finger. So those three fingers you have to stretch in such a way that all three are mutually perpendicular to each other. Okay, so mutually perpendicular to each other. Now you point this your thumb towards the movement. Okay, how you are rotating your conductor, right? In that direction you have to keep, and your finger, forefinger or index finger, you have to point towards the magnetic field. So then the third finger will represent the direction of your induced current. Okay. See here, if you observe this is the direction of rotation. So magnetic fixed direction in this direction. See here, ma. So this is your conductor, AB and CD. Okay. So flux lines are there here in this direction. Okay. So movement will be, so here AB side it is downward, and the CD side it is upward. Okay. So now the direction of current. So you point your finger, thumb finger towards the motion. So that means above side. So then index finger from index finger this side. Okay. So then how you will get, so the direction of current inside this will be inside this CD will be in this direction according to this finger. Okay, or you keep your hands and you observe it. Okay, so here if you observe the second conductor, okay, second conductor, if you see AB, so this is AB. Now it is moving downwards as it is rotating like this. Okay, so your flux lines will be in this direction. This is the flux and this is the movement. Okay, so now perpendicular in the sense, now you have to keep your flux this finger toward from left to right. Okay, so if you take your finger from left to right, and your thumb will be downwards. In such a case, the direction of current, if you observe, so what will be the direction? It will be from A to B, so perpendicular in the okay, like that one. So you use the Fleming's right hand rule or to say the direction of your induced EMF. Okay, so if you apply the right hand thumb rule, we will see that we will see at this horizontal portion of the loop, current will flow from A to B, and on the other side, the other side it will be from C to D. Okay, so in conductor AB it will be this side, conductor CD it will be this side. So the current will be going like this, right? Now still you rotate the conductor, and after some period of time, so that means after 90 degrees again, AB will be downward and CD will be upward. Okay, so from 180 degrees rotation from initially to AB in top, CD is in bottom, so that it is in vertical position. After 90 degrees, you will get like this. Still 90 degrees rotation, you will get this. Okay, so now if you allow the loop to move further, it will come again to its vertical position. So but now upper side of the loop will be CD and lower side will be AB. So just opposite for the previous vertical position. Okay, now at this position, if you observe, the tangential motion of the sides of the loop is parallel to the magnetic flux of the force. Hence, there will be no EMF. There will be no question of flux cutting, and consequently, there will be no current in the loop. Right. So while moving here, so from horizontal position to vertical position here, in such a case, in horizontal position, there will be no flux will be linked, so no amount of EMF will be induced. Okay. So if you further rotate, then again it will start inducing the EMF. Okay. But now the AB side of the loop comes in front of North Pole, and CD will come in front of the South Pole. If you observe this, okay, so AB is coming under the South Pole, and CD is coming. So after rotation, okay, so after rotation, AB will be coming under North Pole and CD will be coming under South Pole. So just opposite to the previous horizontal position. So that means still he rotated this one. Okay, so still 90, 90, and then still more 90. I will place all the okay, ma'am. Again, we will discuss in afternoon sessions. Right, it is already time up. So 10:20 is there. So still we will discuss in afternoon session. Afternoon session we are having the lab, right? So in lab also I'm going to take the class only. So there I will discuss now again this single loop generator, how the EMF will be induced in these AB and CD conductors. Okay, while it is rotating from 90 to so from vertical position to horizontal position, then horizontal position to vertical position, then vertical position to horizontal position, then horizontal position to vertical position, like that. So in one single rotation.
Unable to mic map. ఓకే, మీరు మాట్లాడలేకపోతున్నారా? ఎందుకని అట్లా? నువ్వు మళ్ళీ షేర్ చేస్తా, నాకు లాగౌట్ అయ్యి లాగిన్ అవుతాను. ఒక్క నిమిషం ఆగు.